This time we're going to look at the same substitution but with an extra little step, which involves completing the square to get our original integral into the proper form. So if we look at this integral, the integral of 1 over the square root of x squared minus 4x plus 13, it doesn't look like the square root of x squared plus a squared, but we can complete the square in that quadratic and make it look very, very similar, so that with a simple substitution we can convert it to the form the square root of u squared plus a squared. So for our quadratic, to complete the square, we take half the middle term and square it, and we add it to the quadratic and subtract it again so that the quadratic remains the same. So x squared minus 4x plus 13 is x squared minus 4x plus 2 squared minus 2 squared plus 13. And now that x squared minus 2 times 2 by x plus 2 squared is just x minus 2 squared. And we can convert this quadratic to x minus 2 squared plus 9. Now our integral is the integral of 1 over the square root of x minus 2 squared plus 9, and if we just make the simple substitution or change of variables to u equals x minus 2, then du equals dx, and we're looking at the integral of du over u squared plus 9. Now we can apply our trigonometric substitution. We let u equal 3 times tangent of theta, as prescribed. U equals a times tangent of theta, with theta in the appropriate interval, and then of course du becomes 3 times secant squared theta d theta. Now the square root of u squared plus 9 is the square root of 9 times tangent squared theta plus 9, which, pulling out the 9, becomes 3 times the square root of secant squared theta, which just becomes 3 times secant of theta because theta is between minus pi over 2 and pi over 2. So our original integral was equal to the integral of du over the square root of u squared plus 9, which is equal to the integral of 3 secant squared theta d theta, that's just the du, divided by 3 times secant of theta. And again we can cancel the 3 secant theta to get the integral of secant theta d theta, and this is the natural log of the absolute value of secant of theta plus tangent of theta plus c. And this is very similar to our previous problem. This is equal to the natural log of secant of tan inverse of u over 3, remember theta is tan inverse of u over 3, plus tangent of tan inverse of u over 3. Now we'd like to write this in terms of u first, and then convert back to x. So first of all, trying to write secant of tan inverse of u over 3 as an expression in u, we draw our triangle with an angle theta where the tangent of theta is u over 3. So here theta is tan inverse of u over 3. And that means that the opposite over the adjacent must be equal to u over 3. So if we let the opposite be u and the adjacent of length 3, then we get the appropriate triangle. And then our hypotenuse must be the square root of u squared plus 9, and reading the secant of theta from that triangle, we get the secant is the hypotenuse over the adjacent, so it's the square root of u squared plus 9 over 3. So secant of tan inverse of u over 3 is equal to the square root of u squared plus 9 over 3. Now remember, u was also written in terms of x. U is x minus 2. Finally, we have the integral of dx over the square root of x squared minus 4x plus 3 is the natural log of the square root of u squared plus 9 over 3 plus u over 3, because tan of tan inverse of u over 3 is u over 3 plus a constant, and replacing the u's by x's, we get that that's equal to the natural log of the square root of x minus 2 squared plus 9 over 3 plus x minus 2 over 3 plus a constant.